Now, in this section 2.2, we're about to study my second favorite example of a martingale. So we've seen my first favorite example earlier, and that's a random walk. And what happens with a random walk, like the random walk on Z that you get by adding IID Bernoulli variables, is as the time passes, as you go further and further into the filtration, you have more and more information because your random walker is discovering more and more of its environment. That's a very typical behavior of a martingale. Another very typical martingale of a behavior is when what you do is you have a random variable that you're trying to approximate. That's some of your variable at time equal plus infinity. And what your martingale is doing is giving you finer and finer approximation of this variable that exists at time k equal plus infinity. So we'll see a quintessential example of that we're going to build on just this very simple probability space 0, 1 with the Lowback measure together with the Borel sigma algebra. And this gives you both a very quintessential example of this kind of dyadic martingale construction. This will also be a very helpful example in constructing our Brownian motion, so our basic example of a continuous time stochastic process just afterwards in chapter 3. So let's have a look at what this dyadic martingale look like. Now, the sigma algebra we're going to use is generated by a finite family of sets of Borel sets in 0, 1, which are these so-called dyadic intervals. So intervals of side lengths 2 to the minus k that cover the interval 0, 1, and to avoid having to throw away sets of measures 0, I've made all of my intervals closed on the left-hand side and open on the right-hand side, and I'm working on that set just to avoid extra technical complications. Now, let's visualize these intervals. If k equal to 0, then there's only one of them of length 1. That's the full interval. If k is equal to 1, then there's two of them of length 1/2. That's 0 to 1/2 and 1/2 to 1. And then when k is 2, then we get 4 of those, and k is 3, we get 8 of those, and so on and so forth. Now, the martingale we're about to study is going to be defined in that way, just taking the conditional expectation of a fixed L2 function conditioned on the sigma algebra fk. And what we're going to see is that the function, the conditional expectation of anything given fk has to be constant on any interval in dk. And because of that, really what we're going to get with mk of f is an approximation of f where we are approximating f by something that is piecewise constant on every dyadic interval. Right, so it's a kind of martingale decomposition of a fixed random variable into objects that are piecewise constant, and what happens when you increase k is you're refining your level of approximation. Okay, so we'll need to prove a few basic properties of this. Well, first of all, we need to prove that this is indeed a martingale. It's going to follow very simply from the fact that it's given by successive conditioning on elements of a filtration. So that's a very general phenomena. We'll look at what mk of f look like. Well, it's a finite linear combination of indicator function, the indicators of the set dk, and then what do you do? Which constant do you put in front of this indicator function? Well, just the average of f over that interval. I could almost leave that as an exercise. Well, I could leave that as an exercise, really. And this is a special case of what you've seen before when you've proven that a conditional expectation, when you're conditioning on a finitely generated sigma algebra, looks exactly like this. But we'll have another look at that in the proof of this proposition. We'll show that mk of f has to converge to something almost surely in L2. You can tell that this is a consequence of the Dubs martingale convergence theorem. All we need to prove is that this martingale is actually uniformly in L2 in order to get the conclusion of 4. Now the question is, well, this limit of the martingale, well, is that going to be the function f or not? I mean, that's what we expect, right? That we are approximating f by something that's piecewise constant and equal to the average of f on the interval. My drawing is actually a bit misleading because it looks like I took the value on the left. I should have taken the average of the values of the interval to be precisely mk of f. Now, we're not going to be able to prove that directly. This takes 2 steps, and the first step is to show that this holds at least if f is continuous, and then we're going to have to, in order to prove that it holds for every f in L2, we'll approximate elements of L2 by continuous function and see that this is compatible with this limit, but that will be the content of the next theorem. Let's prove this little proposition to start with and get the properties of this dyadic martingale right. Okay, so we have this mkf, which is just the conditional expectation of f given fk, f being an element of L2. I want to show that this sequence mkf forms a martingale with respect to the filtration fk. Let's first show that f is in L2 and mkf stays in L2. That follows from Jensen inequality in the following way. If I look at the expectation of mkf squared, well, that's the expectation of a conditional expectation squared. That's by definition of that's by definition of mkf. And then when I apply Jensen, because the function x goes to x squared is convex, this conditional expectation of f given fk squared is smaller than the conditional expectation of f squared given fk. And now I can use the fact that the expectation of a conditioned variable is always just the expectation of the variable. Right. And notice that this tells me that if I could take the supremum over all j and n of the L2 norm of the mjf, this would have to be smaller by this reasoning just above to the L2 norm of f. So mkf stays in L2, and in fact it's uniformly in L2, which is going to be very helpful to apply the Dubs Martingale convergence theorem and get 0.4. Now notice that that I have a martingale thanks to the tower property. I need to check that the expectation of mkf plus 1 given fk is mkf, but the tower property is exactly telling me that, right? That the conditional expectation of a conditional expectation is just the conditional expectation given the smallest of the two sigma algebra, which is fk here. So this was the conditional expectation of mk plus 1 of f given fk, and this has to be equal to mkf. So 1 holds, and thus and I should not say thus, and by a star 4 follows from Dubs Martingale convergence theorem. Okay, that's 1 and 4. Do we have 2 and 3? So this description of mkf as being a finite linear combination of the characteristic of the indicator function of the elements of dk. Yeah, that's also reasonably easy to see. Let's do it. Let's fix a j between 0 and 2 to the k minus 1. I fixed the length k. Now I need to integrate over this interval j 2k to j plus 1 2k what I think the conditional expectation should be, which is this linear combination of indicator function, and then check that it does the job. And if it does, then it has to be the conditional expectation picked by uniqueness of conditional expectation. Now notice that in this sum only one term is non-zero, because this is 0 unless I is equal to j. Right, because the intervals in dk form a partition, they do not intersect. So what I have here is the integral j 2k to j plus 1 2k of 1 upon 2 minus k times the integral I to k I plus 1 to k f of t dt dx, and this, because these intervals have lengths 2 to the minus k, this is exactly, sorry, that was j, that is exactly equal to the integral from j to k to j plus 1 divided by 2k of f of t dt. So I've proven that this function here exactly satisfied the definition of a conditional expectation. It's equal on every interval in dk to the integral of f over dk. Now, what does that tell me? That tells me exactly that e of f given fk, so my mkf, is equal to this sum by uniqueness of conditional expectation, very similar to an exercise you've already done. Okay, and that proves 2 and 3 using the fact that given any point there's a unique interval in dk to which that point belongs to, because again I have a partition. Okay, now there's one last thing we need to prove in this proposition, and that is that the limit that we get from the Martingale convergence theorem is equal to f. And as I mentioned, we're not going to prove it at the level of this proposition for all f in L2. We're purely going to prove it for f that is continuous, and then the next theorem will extend that result to all elements of L2. Okay, so why does that hold? Well, let's take a, so that's 0.5. Let's take a g that's continuous on 0, 1, and I'm going to call it g rather than f just to avoid confusion. No, that g is continuous, so it's going to be uniformly continuous, and I'm going to look at, given a k again, the mk of g at a point t minus g of t, and I want to show that for every t in 0, 1 actually this goes to 0 as k goes to infinity. If I can do that by uniqueness of limit, pointwise limit, g would have to be m infinity of g. Now what is this? Well, we've just computed what that is. So given a t, I'm going to pick it in dk such that t is in it. There's a unique interval that does that. And then I'm integrating over it, which is an interval of length 2 to the k, my g of s ds. That's exactly what this conditional expectation is, thanks to point 3. And then g of t, well, it's a constant, and I might as well multiply it by 1. Such that we can see this as being smaller than the average over it of the absolute value of g of s minus g of t. But this is the difference between two values of g, s and t, that are both in t, in it, and it is an interval of length 2 to the minus k. So this whole thing here is certainly smaller than the supremum over all possible of s and s prime over the interval 0 minus 1 that are close together. The distance between the two can not be more than 2 to the minus k. You can vary s as much as you want over the interval it. You're never going to get further than 2 to the minus k from t. Okay, but that's exactly the definition of uniform continuity, that this goes to 0, since g is uniformly continuous. That's uniformly continuous because it's continuous on a compact interval. And that concludes the proof of this little proposition. So mkf, conditioning on the interval fk, and put in another way, replacing the value of the function by its average over a dyadic interval, will converge back to the function at least when the function is continuous. Now that we've seen this, we're going to prove our next theorem that says that actually this holds for every f in L2 of 0, 1. And this is called the Lowback differentiation theorem, and that really tells you that up to a set of potentially measure 0, when you take the average of the function over a smaller and smaller dyadic interval, the limit exists and is equal almost everywhere to the function itself. Right, so let's prove this Lowback differentiation theorem. Now, what do we need to prove really? Well, we need to prove, we know that the limit m infinity of f exists, we just need to show that it's f. So what we need to show is that the probability that the limbs, well, yeah, the limit, we know it exists, of mk of f minus f being positive as k goes to infinity is 0. And now we can remark that this probability of being greater than 0, so the limit not being f, is certainly well, it's equal to the probability of the limit of the mkf minus f being greater than 1 upon n, say, and I can take the union over all n in n of that. Right, so if you're greater than 0, you're greater than some 1 upon n for n, an actual number. And now the point is that I'm taking a unions of sets that is countable. It's a countable union. So if I show that the probability of limits of mkf minus f being greater than 1 upon n is 0 for all n, then I'm going to have a countable union of set of probability 0. This has probability 0. So this would imply that m infinity f is f. So I only need to show this, right? I only need to show that the probability of mkf minus f is being greater than some fixed number is 0. Now, just to make the argument neat, we're going to show that the probability of the limit of mkf minus f being greater than 3 alpha is 0 for every alpha positive. Right, so check it out. You can take alpha equal 1 upon 3n, and that would give you the result for any n natural number. You'll see the point of the 3 in a minute. That's because we're going to cut into 3 bits, approximating f by an element g that is continuous. So let's give ourselves an epsilon, and let's pick a g which is continuous on 0, 1, and approximate our f in L2. This is possible because continuous functions on 0, 1 are dense in L2, as you would have seen from the construction of the L2 space. Okay, so I'm picking such a g, and I need to prove that this probability cannot be large. Now notice the following, and that's the point of the 3. I need to consider the expectation of f given fk, say at a point t, minus f of t. And I can cut that in 3 in the following way. I can take the expectation of f given fk minus the expectation of g given fk, and then I can subtract expectation of g given fk minus g, and then I can take g minus t. That's just triangle inequality. But the point of doing things in this way is that in the middle here I have something that I already know goes to 0, and then the other two terms should be very close to 0 too, not so much because k goes to infinity, but because f minus g is small in L2 norm. So let's see how we exploit that. So what have we got? We need to compute the probability that the limit of mkf minus f is greater than 3 alpha as k goes to infinity. Now, if this is greater than 3 alpha, okay, I'm gonna show in fact that I know that the limit exists, so it's equal to the lim sup, and so this can only happen, okay, on a set where this happens, if this is greater than 3 alpha, then one of these three things has to be greater than alpha, right? If all three of them were to be smaller than alpha, then this would be smaller than 3 alpha. That was the point of the 3. So really this probability set where the limit is greater than 3 alpha is included in the union of 3 sets. The sets where this is greater than alpha, this is greater than alpha, and this is greater than alpha. Now that tells me that the probability of the limit being greater than 3 alpha is smaller than the probability of, well, let's have a look at what the first set is. This is the set of things where the limit, we know that this limit exists, as k goes to plus infinity of mkf minus mkg is greater than alpha. The second set is the set where the limit of the expectation of g, I should just call that mkg minus g, is greater than alpha. Now, but we know that this is 0 already by 0.5 of the proposition, and then we have plus the probability that just f minus g is greater than alpha. But that set cannot be very large because f minus g is small in L2 norm, so it cannot, f and g cannot differ from each other on too large a set. So we're going to exploit exactly that. So for the first term, okay, we need to remember what that is. So this is the probability that the limit, and probability that the limit is large is certainly smaller than the probability that the supremum is large, of mk of f minus g is greater than alpha, plus what I'm going to do with this term probability of f minus g being greater than alpha, I'm going to remember that this is smaller than 1 upon alpha times the expectation of f minus g, sometimes called Markov inequality. That's just because this probability is the expectation of the indicator function of that set, this set where f minus g is greater than alpha, and on that set, well, f minus g divided by alpha is greater than 1. Now, here I'm going to apply Dubs. That's what we call the weak type 1-1 inequality. So this mk of f minus g is a martingale, right? That was point 1 of the proposition before. So Dubs' weak type 1-1 inequality tell me that this is also smaller, because I have a martingale, than 1 upon alpha times the supremum from k in n of the norm of f minus g. Sorry, the L1 norm of f mk of f minus g. Right, but the reasoning we've used to show that mk of f is uniformly in L2 actually also give us that it's uniformly in L1, because this is the supremum of a expectation of a conditional expectation, and because absolute value is a convex function, you can apply Jensen to this, and the fact that the expectation of a conditional expectation is still equal to the expectation of the variable. So this here is smaller than 2 alpha times the expectation of f minus g. But now, by Cauchy-Schwarz, if you want to, by the fact that in probability L2 is always included in L1, this is smaller than 2 alpha times f minus g in L2 norm in L2 norm. And we've seen, well, by definition of the way we've picked out g, this is small. This is smaller than 2 epsilon over alpha. Now, epsilon was arbitrary, and so therefore I can send it to 0, just picking my g appropriately, and that gives me that the probability that the limit of mkf minus f is greater than 3 alpha is 0 for every alpha positive. And that concludes the proof of the Lowback differentiation theorem. So we've seen that the dyadic martingale that you construct by taking conditional expectation on the filtration generated by a dyadic intervals of 0, 1 gives you an approximation in L2 of any L2 function. Now, we'd like to understand the nature of that approximation a little better, and what we're going to show is this beautiful result in my maybe analytic perspective, that such a decomposition of f into a martingale is actually a decomposition into a basis, so something very fundamental to analysis. So we'll find that there exists a certain basis, it's called a Hbases, orthonormal basis of L2 of 0, 1, such that what we're doing when we are averaging the function of a dyadic interval and taking linear combination of those, so when we are doing this probabilistic decomposition of f, we're doing an analytic decomposition projecting onto a basis. Okay, that's going to be very helpful also down the track. So again, it's interesting in its own right that actually a martingale decomposition, if it's a dyadic martingale, is a incarnation of the decomposition of a vector into a basis in linear algebra, but it's going to be particularly helpful in constructing the Brownian motion, because we will use this basis and put some random coefficient on the basis in order to construct the most important stochastic process in this course. Now, what is this Hbases? Well, it's constructed in the following way. So you start with a function which is 1 on half of the dyadic interval 0, 1, and then minus 1 on the other half, right? So it looks like this. Here is 0, 1, is 1 half. You put a 1 here and a minus 1 there. And let's define it on all of R and put it to be equal to 0 everywhere else. We also need to initialize our family of half function in order to have a basis, and we initialize it with h naught being equal to 1. And then what we do, and that's a special case of something called a wavelet construction in analysis, which is a very important tool in all sorts of approximation arguments, is the following. So we do some translation and some dilation. So we dilate by a factor 2 to the k, and then we translate. Now, what does that mean really? It just means that the family of elements of the Hbases h2k, they all supported in a dyadic interval in the sense of the dyadic intervals in dk that we had before. So what we're getting is that a typical R function will look like this. You have a certain decomposition at a level k, so this is of length 2 to the minus k, and then in such an interval, if you zoom in, you will see the half function being equal to 1 on the left hand side of the interval and minus 1 on the right hand side of the interval. So what I've drawn here is the R function h2k plus 1. h2k 0 will be the one on the very first interval. h2k plus 1 is the one on the second interval from the left of side length 2 to the minus k. Right, so this is what these functions are. And what we're going to prove about them is the following. We're going to prove that on a dyadic interval, the martingale difference, and remember that the limit of the martingale is the sum of the martingale differences, is exactly equal to the inner product of the function with the our basis, our function corresponding to that interval multiplied by the function. So really what we're doing here is that we are projecting f on the subspace generated by just this single half function. Right, as a consequence of that, we'll get what I was saying, that the conditional expectation of f given fk is a linear combination of half function with the coefficient being the inner product of f with the half function. So let's prove this lemma. I'm going to fix an interval I. It's a dyadic interval, an element of dk, so it's something of the form I divided by 2k to I plus 1 divided by 2k. K is fixed and I is also fixed between 0 and 2k minus 1. And I'm going to give some name to the left-hand side and the right-hand side of that interval. Might as well call the left-hand side I plus, because that's where the half function is going to be positive, and I minus for the right-hand side on which the function is negative. And notice that these are elements of dk plus 1. Right, so I need to compute on this interval I the martingale difference mk plus 1f minus mk of f. So what is this? Well, it's the indicator function of I. Okay, what is mk plus 1f going to be like? Well, it's going to be the indicator function of I plus divided by the length of I plus, integrating f over I plus, and then the same thing over I minus. Right, that's it. The proposition we've seen before. You just get a piecewise continuous function with indicator functions of the elements of dk plus 1, and I plus and I minus are the only elements of dk plus 1, the only elements of dk plus 1 that intersect I. Right. Any other element of dk plus 1 will be in another interval of dk than I, and so multiplied by the indicator function of I will be 0. Okay, that's my mk plus 1. That's my mk plus 1 of f on I, and then on I, mk of f is just the average over I of f. Sure, because I is already an element of dk, so f is constant on that interval. Okay, so now let's try to group things together a bit. Now I have here an indicator function of I plus. I'm going to divide, what is that? So I'm dividing by 2 to the minus k plus 1. Integrating over I plus, and I have over I minus the same thing. And then here, let's see what happens on I plus, and let's see what happened on I minus. So on I plus, I'm integrating over I plus, and I'm also integrating over I minus. And then same thing on I minus. Okay. Now let's try to group these things together and see what we get on I plus and what we get on I minus. So on I plus, we get 2 times the integral of f on, so if we normalize by 2 to the minus k, we get 2 times the integral of f on I plus from here. And then we get minus 1 time there. the integral on I plus, and minus the integral on I minus. Okay, and what do we get on I minus? Also normalizing in that way, we get 2 times the integral on f on I minus, minus the integral of f on I plus minus the integral of f on I minus. Now combining all of these gives what? Gives the integral of I plus 2 minus k, integral of f over I plus minus integral of f over I minus, and then minus indicator function of I minus divided by 2 to the minus k times the same thing. That comes with the opposite sign here. So what I have is indicator function of I plus minus indicator function of I minus divided by 2 to the minus k times the integral over I of f times the indicator of I plus minus the indicator of I minus. But what is that? Well, this is exactly equal to this is the half function, f times the r function, h2 to the q plus I, that's the inner product. Here, appropriately normalized, so to appropriately normalize, I need to divide by 2 to the minus k over 2. That's to make the r function have L2 norm 1 times the half function itself. And that proves 1. Excellent. Now, to prove 2, we need to see what happened when we sum up these martingale differences. Well, when we look at the expectation of f given fk minus the expectation of f given f naught, that gives us the sum from L equals 0 to k minus 1 of the conditional expectation of f given fk plus 1 minus the conditional expectation of fl plus 1 minus fl, and we've just computed what these things are. So these things are what? These things are the sum from L equals 0 to k minus 1 of the sum over all dyadic intervals of side lengths 2 to the minus L. Alright, because they form a partition, times the martingale difference, ml plus 1f minus mlf. And we've just computed what these things are. These things are just the projection onto the corresponding elements of the R basis. H2 to the L plus J, H2 to the L plus J. Okay, but this is just a specific ordering of the Hbases, rewriting every natural number n in a dyadic way, and well, sorry, in something of the form 2 to the L plus J for some L in n and some J between 0 and 2 to the L minus 1. So this is exactly equal to the sum from n starting at 0 and going to what is it going to be when we reach 2 to the k minus 1 of f hn inner product hn with hn. And that concludes, that almost concludes the proof of the lemma. We just need to realize what the expectation of f, sorry, this was not starting at 0, this was starting at 1, and then we need to realize what the expectation of f given f naught. Well, what is that? It's really, because f naught is the trivial sigma algebra, so it's really just the integral of f. But what is the integral of f? Is the inner product of f with h naught times h naught, because h naught is the constant function, equal to 1. And now that concludes the proof. Okay, so to finish this chapter, we're going to have a little theorem that tells us that this Hn, this half function that we've just defined, form an orthonormal basis of L2 of 0, 1. That's really a consequence of what we've done so far. So the proof, first of all, Hn, Hm is equal to 1 if n equal to m. Well, that's obvious because we're just integrating 1 over an interval of a certain side length, and we've divided by the square root of that side length that normalizes things in L2, and 0 if n is non-equal to m. Now, I'm going to leave that as an exercise because that's a very good way to get a feeling for how these half functions behave, but this is fairly simple. Now, obviously, if you have two half functions that are on different interval, then the inner product will be 0 because the support of Hn and Hm do not intersect. And then if they are located on the same interval, but they are at different scale, then one of them will be equal to 1 on this interval, and then the other one, the one that corresponds to a more refined scale, would be equal to plus 1 on half of the interval and minus 1 on half of the interval. Or it could be that there's even, that's if there is a difference of 1 in scale, but if there is an even further difference, what you might have is that 1 is just plus 1 on a tiny part of the interval, minus 1 on another tiny part of the interval. But the point is that on the support of the smallest one, you're integrating something that is 1/2 of the time and minus 1 the other half of the time. Therefore, it has to be 0. The integral has to be 0. So I'll let you write up this argument. That gives you the fact that you have an orthonormal sequence. And now, is it going to be a orthonormal basis? All you have to show is that it really spans the entire L2 space. But why does it span the entire L2 space? Well, that's thanks to the Lowback convergence theorem. We've seen that for any f in L2, f is the limit of the Martingale decomposition into the filtration Fk, and that is really equal to the limit of the Martingale differences. So this is the limit as k goes to infinity of the mk plus 1 of f minus mk of f, and then mj plus 1 minus mj of f, j running from 0 to k. I should have said my f may not have integral 0, so let's subtract the expectation of f, which is really m0 of f. Now, so NF can be written in that way, and now we've seen that this is a decomposition into the Hbases. So this is the sum j equals 0 to 2k minus 1 of f hj. So we know that this decomposition into the Hbases will converge, and it will converge to f minus expectation of f. So Hn, the span of all the Hn, has to be all of L2, because any element of L2, you subtract this, which is just changing the zeros coefficient, can be written in that way. The span and take its closure, because you're taking a limit of this finite linear combination. So Hn spans the entire space, an orthonormal family. It therefore has to be a orthonormal basis. Right, so this concludes today's chapter on discrete time martingales. Let me remind you that we've seen two quintessential examples of a martingale, sum of ID variables or random walks. More generally, we've seen that we can modify these examples for things like martingale transform. We've seen that martingales have very nice size and convergence properties. Their probabilistic properties imply very good analytic properties, such as uniform boundedness in L2 implies convergence in L2. And we finished off in this section with another quintessential example, which is a dyadic martingale. So you take a a random variable in your probability space, and you successively, in a dyadic fashion, approximate it in finer and finer ways, with the zeroth level of approximation being approximating by just the mean, by a constant random variable. But then you refine that, and in that context of the probability space being 0, 1, we've seen through the Lowback differentiation theorem that the limit not only exists, that's the Martingale convergence theorem, but is the random variable f you started with. We've seen that this has another description in terms of decomposition into a basis. So we really, the Martingale perspective on the function corresponds to an analytic or a linear algebraic perspective of decomposing into a basis. Now we're going to use this basis in the next lectures to start constructing continuous time stochastic processes as limits of appropriate discrete time processes, and the very first one will be the Brownian motion.